Hi, I'm Robert, and today I'm work at Parity Technologies as a core engineer. And today I'll talk to you about BEEFY, or very specifically, and not much else about BEEFY, even though you may like updates from anything else, how to make the proofs small, and just the data structure side of that. So what's our vision? And when I say what's our vision, what do I want, and what do I project that you also want? What the space is doing as a whole. So for me, the primary the first goal is to prevent abuse of power. That is why we put up with all this nonsense where we verify things everyone else does, and when we have permissionless systems. The other thing that we want is to facilitate coordination between agents that would otherwise be unthinkable in a setup requiring trust. So if we started from this basis, then in the utopia, what we require is that everyone runs a full node. That is, that everyone verifies what everyone else does, and in that case, this can actually be trustless. Unfortunately, the reality, or at least the path that we've built so far, is built on beanbags. So primarily, the one that we always think of is Infura. That is like one of those instances where we could be trustless, but instead everyone is fine with just using Infura. Block explorers and MetaMask are other big examples, but foremost, leaving funds on centralized exchanges. Many of those, well, not all of those would be solved completely by running full nodes, but they would at least be mitigated. So the reality is that running a full node is hard. Anyone trying to run like a Polkadot or Kusama validator knows that it requires a lot of resources. So to build a trustless world, maybe we have to lower our standards a bit and go for a more pragmatic solution. And light clients, in this case, are one of these pragmatic solutions that allow us to get to the trustless future with actually getting this into the hands of more users. So how are they, what is superior about light clients? They require lower storage and lower computational requirements onto users than full nodes impose. And the way that you usually go about this is that if you run one of these nodes, or if you run a light client, you only verify what concerns you, not everything else, which is what full nodes typically do, is that they verify everything, not just a subset of things that are of concern to the user. And that's the design principle that we're going to pursue here. I'm going to switch gears a bit and talk about bridges for a moment. So bridges very similarly have been dominated by problems coming from centralized setups with multi-sig, mostly traditional bridges involve multi-sigs. And there's been a plethora of hacks like the last few years. There was some nice statistics that Alistair showed in his great talk earlier. I think it was around half or so of the 3.8 billion that were lost, of the major hacks that we've had so far that were just due to bridges. So this is no bueno, and to get around this, we need to build a truly trustless bridge. And whoopsala, this actually intersects with light clients, because if you want to run a fully trustless bridge, then this actually operates by having light clients on both sides that mutually verify one another. It's actually the extreme form of light client design, because you're working in one of the most computational and storage constrained environments that you can think of, which is a blockchain. And also, this light client, what makes solving this problem even more critical is that, unlike the light client that you may run on your phone, this is not just for one single user. If you say you have two chains and you run the gigachad of bridges that actually does all of the activity between them, then then you can't afford any trust in the setup, because it can affect the funds of all users who go cross-chain here. So how to light client then, if we want to use this ultimately for bridges? So the general design principle that I already mentioned is that every agent only verifies what concerns that agent, or in the cases of a bridge, that we only verify what pertains to funds going across the bridge. Not looking so granular, like we can say we only look at the blocks that actually concern us, and we only do these in some epochs, for instance. And then for light clients running on-chain, we also need to optimize the computational complexity. So ideally, we want our operations to be constant time, but at least they should be sublinear where possible. This also matters for light clients that are not online all the time. So if they need to catch up with the latest state, or in the case of a light client like a bridge, where you're only going to sync some of these blocks, there at least we want to be sublinear. So two useful primitives that everyone working here will have worked with so far are like blockchain. So they have two interesting features. So on one hand, we have blockchains who have order one append operations. That is one feature that we'll want to preserve while getting rid of some of the other less efficient features of blockchains. And on the other side of the spectrum, we've got Merkle trees, which allow order of log n membership proofs. Now, when I prepared for my talk this morning, I was a bit scared, so I had two visitors who said they would help out. Well, one of them is not going to help, and we're going to try to get rid of him. But first, we have good grandma Gabriela. So what's great about Gabriela is that although she looks quite old, she lives in the now. She tries to take life one step at a time, and she also doesn't let the past drag her down. And she's going to be the hero of the story, and we're going to try to build a data structure that satisfies her needs. On the other side of her, and we have bad baby Bruno. So this line there, develop focus and logical thinking, that's pretty aspirational for Bruno. He isn't quite there yet. He's a destructive little guy, and he wants to push over all those dominoes, despite all the pain that this will cause Mama or Gabriela to clean up later. So he's the antagonist that we'll try to beat. So I'm going to try to give you the sword to, well, let's not kill Bruno, but let's not let him have his way. All right. So what we'll cover today is go first through traditional light client design, which is SPV proofs, or like SPV setups, which have existed since forever. Then there's from Peter Todd, like, which I'm sure most of you will, well, who here knows what MMRs are? That's a pretty significant portion of everyone here. Yeah. So MMRs have become popular for light clients or for like a multitude of reasons. So on one hand, yes, because the membership proofs that they provide can go logarithmic in n. I'll say later what k is. And then the bulk of my talk will focus on great research by Alfonso Ceballos and Alistair Stewart from the Web3 Foundation, which is firstly FMMRs, which stands for forward bagging MMRs. That's going to be the first step. That's going to have some benefits, in particular that it's going to have O1 append operations if we amortize. Then we're going to go over to unbagged Merkle Mountain Belts, the forward bagged ones, and eventually the normal Merkle Mountain Belts. So let's start off with SPV clients. So what I'm showing over here is a blockchain where we say that this over here is the tip of the blockchain, and we want to do a membership proof of some leaf that is stored in some other block, which could, say, be a transaction. So Gabriela is featuring here because we're simultaneously doing two things, one of them that she likes and one of them that she dislikes. So the complexity, so now for like a, if we want to look up this particular block, this block is going to have depth k, so we're going to be like doing order k, like if we want to like do that lookup to find that state tree over here. So that's great if we're looking at something that's very recent, which, as we said before, Grandma Gabriela lives in the now present, so we care more about things that are recent than old. So that's a nice feature of it. But also it's k, it's not like logarithmic or anything. So if we go a little bit deeper, then this increases the amount of steps that Gabriela has to walk to get there. So that's the one feature that I mentioned before of blockchains, the order k like lookups, and but also like if we add one block that's that append operation is just we just add the block, we don't do anything else. So that scales pretty well. And then once we get to the actual block where we want to look something up, there we could, for instance, now here use like a normal Merkle tree and then have a membership proof for items in there. So I'm marking those things bright green, the proof items. So if we want to look at leaf 6 here, over, for instance, what we'll need to prove the membership of it is leaf 5. Then of the nodes, we need the one that's hashing nodes 7 and 8. I'm going to use this notation whenever I'm hashing something, hashtag, and then the set of things in between with everything in the middle abbreviated, and this one over here. So that's going to be order of log n to have a membership proof for that leaf. So SPV clients already show some of the things that we want, but we can improve upon this. So that's the concept of MMR. I'm just going to give a high-level description here and later look at the representations of it. So MMRs, in principle, so one downside if we have a Merkle tree is that it will always have to be completely balanced. So if we have like number of leaves that's not a power of 2, then we'll have to add dummy nodes to make this a full Merkle tree, unless we go for Merkle Mountain Ranges. Ooh, this jumps a bit far. With those, what we do is that instead we build incrementally, we build full Merkle trees and we bag them together at the top. And what we do in Merkle trees, so then we have peaks that sit at the, I already showed this, we have peaks that sit at the top of these Merkle trees and we bag them together from left to right. No, wait, from right to left. So what we can see here, for instance, if we have something, this would already be like a Merkle tree. Once we add another leaf, then we can hash them together to form like a Merkle tree. When we go, so that's still a power, those are still like powers of 2, those are fine. If we go to n equals 3, now we need to do this bagging process where we bag together these peaks. And over here, these, and this proceeds again, so here we have a power of 2 again, so now we can form a full Merkle tree. We bag those together, yada yada. Now, it gets more interesting. Right, so this is the first time that bad baby Bruno features. So what is a bit unfortunate with the way that these MMRs work is that whenever we append something, we destroy the entirety of our ephemeral bagging, so these bagging nodes. So if we look at the step here from n equals 6 to 7, already for these simple trees we can see it. We bag everything at the top there with the hash 1 to 6. But then when we add this one leaf over here, we have to get rid of this bagging node and replace it because we're doing this bagging here from right to left. And yeah. So, right. Membership proofs, on the other hand, have the same nice benefits as like with normal Merkle trees, is that they go with log n, or like the supremo of log n here, because it doesn't have to be a power of 2 anymore. So here we're trying to prove leaf 6, and we have to add those 4 items here to get to the root of our MMR. Oops. And like now, for instance, for the last leaf over here, that still holds. So this one requires, the one for leaf 15 requires fewer leaves, so that, but we can still do better, which we'll do with the later data structures. All right, so now there's one unfortunate thing that we saw before just now, which is where we had to discard all of the ephemeral bagging we would like to get rid of. And what, for instance, now if we were to reverse the order of our bagging? Now, this is going to lead to a less balanced data structure, but it's going to have the benefit that more recent things are going to be closer to the root than there would be in a balanced data structure. And so while this is less efficient on the data structure side, mostly when we want to prove things, it's about something that's recent, not something that's very old, especially if you think about something like the state of a blockchain or so. You don't do these historic lookups, you look at what is the current state. And this is even more so the case in if you don't have, in the UTXO model, there's arguments to be made why that you're still going to be querying old things, whereas in Ethereum and Polkadot, that's not the case. All right. So in this case, the only thing that we're going to do now is we're going to change the bagging to go from left to right. And what we have happening here then is it looks completely similar now when we only have one bagging node. But once we add 2 bagging nodes, we can see that Gamma Gabriela here is happy because the bagging node here, hash of 1 to 6, we can preserve there when we add leaf 7, which we couldn't do before in the normal MMR. Unfortunately, she gets unhappy again over here because when we append the 8th leaf, we have to create this node here, this node there, to get to the final one. So we have to create 3 ones here, so like log n in this case. And so while we've already improved here by being able to preserve some of the ephemeral nodes, this is still something that we would like to change. The membership proofs then also so as I mentioned before, we get less efficient, so our membership proofs gain up to a factor of 2 for the proof items, because we now do this unbalanced bagging over here. We see that if we're looking at like an old leaf here, so like 6 for instance, then which was previously closer to the root, now because we're preferring having shorter distances for the recent leaves, we have much more proof items to add here. On the other hand, of course, if we look at leaf 15 now, then we only have to add 1 extra proof item if we want to create a membership proof for it. So we're moving in the right way, but we still have a bit to go. So now I move over to UMMBs. Over here, we will get rid of the bagging structure that we had before temporarily. Well, in the other data structures, these are still valid in their own right. So what we'll do is, what I mentioned before here when we looked at over here, when we go to n equals 8 and we had log n, so in this case 3 hashing operations to perform, we would like to only do 1 for every step. As I said before, Gabriela takes life 1 step at a time, and by doing this, we can like bound the computational cost much easier. So in the unbagged Merkle Mountain Belts, we won't be bagging any peaks, which means that our accumulator here will now be log n, not in more constant size, so not just 1. But yeah, our appended procedure will be, we will only like do 1 merge operation whenever we add a new leaf. And in combination here, we'll be optimizing the membership proof sizes too, when we don't bag these peaks, which you'll see on these slides. So the differences to point out here to the MMRs, the MMR flavors that we've seen before here, we can already see this when we go to n equals 4. Before we would have merged again 1, 2, and 3, 4. But since we only do 1 step at a time now, we leave those as they are. When we add the 5th leaf, now we go for the right. So what I forgot to mention is that we always only do the rightmost merge that is possible. So when we add leaf 5 here, then we perform this merge lazily. And then, right, over here nothing interesting happens. And then we see this difference against MMRs come about again, the laziness here. When we add the 8th leaf, we could now be building a full Merkle tree, but we don't, since we only perform this merge here from n equals 7 to n equals 8 and nothing thereafter. And when we add the 9th leaf, we again don't merge these 2 trees fully, we only add 1 merge step. Something that we can see emerging here is that by only doing this lazily, if we view our accumulator here as just being the set of peaks, then when we do these membership proofs, so for something that's old, now we only have to do, right, so if the accumulator includes all of the peaks, then we only have to, for like proving a leaf, we only have to prove its path within its local Merkle tree that it sits in. So for leaf 6, we only have to take these membership items. We don't have to take those 2 peaks anymore. And we can reframe this picture now of the complexity by the distance of the leaf that we're looking at from the tip of the chain, or the tip of the most recent leaf. So in this case, it's going to be bounded by log k. Maybe this is more visible if we move to like a recent leaf. So here for 12, for instance, so here we've got a distance of 3. And if you're a recent node, in the worst case, you're going to be sitting in the most recent Merkle tree, and in that case, the biggest that your tree could be is log k, so the distance of you from the most recent leaf. So we see here that as we move closer and closer to the tip, we require fewer and fewer membership. Oof, this thing jumps around quite a bit. As we go to more and more recent leaves, now we need 3 items, so like upper bound of log k here. Now we only require 2, here only 1. And then when we try to prove the most recent leaf for this particular tree, we don't require any membership proof items anymore. The cost at which this came is that now we have this log n size accumulator. So maybe we should reintroduce the bagging. And that's what we'll do with the FMMBs. So we'll regain this order 1 accumulator by still doing the same things that we did with the UMMBs, which is to only perform 1 merge step at a time, and to then do the same as we did with the FMMRs, which is to bag the peaks, also in this case from left to right. So we'll see that the worst case we don't improve, but the amortized one, just like with the FMMRs, we do improve upon. And unlike with the FMMRs, also our membership proofs are going to be logarithmic to the distance from the most recent leaf. So I show the evolution here again. It doesn't have any differences at this stage because, like the against the UMB. So what you see at the bottom here, up until the peaks, and I also see that my legend is not showing it all. Well, anyway, so maybe I should take the chance to explain the color coding. So leaves are this purple over here. Peaks are always the green. I don't know what this shade is called. It's not the best green. And then the neon pink red is always the ephemeral bagging nodes. Yeah. So at this size, we don't see any difference aside from the, we see the difference against the FMMRs for this one here, for instance, because now the what would previously just have been the peak for one Merkle tree, now this part remains ephemeral, and we just have two smaller Merkle trees of the same size, which disappears in the next step when we actually perform that one merge. But what we see later is the same as we saw with the FMMRs, which is that we can preserve our bagging, and we can do so better than with the FMMRs. So here we're preserving, for instance, throughout this entire process, we're preserving the one that hashes 1 to 6. Now, what we don't fix yet is the worst case append, and specifically if we're trying to build a bridge, this is something that and if we're running in a very constrained environment like running on the EVM, then this is something what you optimize for. So I'm going to switch notations over here. I'm going to switch out I'm going to start hiding the leaves now and the intermediary nodes and just focus on the peaks and on the bagging nodes. So what the numbers here will mean in our notation is the height of said peak. So the one 1 to 4 over here, for instance, that one has got height 2. This is height 1, and this one has height 1, 2. And then for the range nodes, we just represent them like that. Here you can see my legend again. Finally, it's back. Okay. Right. So if we switch to this notation, now we can start looking at some worst case behavior. And now this also allows us to look at much, much bigger trees, which are actually closer to what we would be doing in practice than these tiny tunes. So what I'm representing here is an append procedure where we're adding a new leaf, which is the 0 over here, and it's not added yet. That's why the line is in blocks. So now when we want to add this leaf, we will just be merging the rightmost mergeable pair. So the mergeable pairs that we can see here are these two peaks of height 9, the two of height 6, and then the two of height 1. And we'll only be merging the rightmost one. So we perform this merge, and then what I express with the color coding over here is all the hashes that we have to update. So what we're doing is we're doing this bagging from left to right. So we only have to update the ones up until the most recent leaf. So it will affect these two only. That's not so bad. Now, let's see. Yeah, then in the next step, so up there I show the numbers. So we've got a leaf count of 1,341. So when we add the next one, the next mergeable pair is this new leaf that we're adding and the peak of height 0, which is just a single leaf. And then we merge those. And then in this case, we only have to update one hash. So this looks pretty good. But the problem comes in when we now add the next leaf. And now we see that the next mergeable pair we have sits quite far away from the most recent leaf. And this is where baby Bruno kicks in, and he really wrecks our life because he knocks over all of these dominoes. So just when we have to do this merge here, we have to update all these hashes as we go back to the most recent peak over here. Now, how do we resolve this? How do we prevent baby Bruno from having his way? What we do, which is the trick that's the main trick of MMBs, is that we say, well, what if we split up these range nodes into their own separate ranges? And what we want to do is that we still acknowledge that we want to be doing these merges of peaks of the same height. But we're going to segregate after, in every case, we're going to split these ranges after every pair of mergeable peaks. So the first step that we get now, that we see that we get 3 ranges for this data structure over here. Now, these are sitting separate again, and we're going to tie those together with what's called belt nodes. So that's why so if you also look at the peaks look like peaks, then the rhombi here are for the ranges, and then the belt is for the thing my dad used. No, that looks like a belt. Yes, so now we can still, by introducing these belt nodes, we can still have this order 1 size accumulator. So now when we look at this same step that we looked at over here before, which looked so bad because we had to update all these hash values there, when we now perform this process, thanks to splitting up these range nodes, we don't get this infectious domino effect, but we only have to update the hash over there, and we have to update the value of the 2 range nodes, and of course, because we added this leaf over here, this one still has to be updated because it's being added. Cool. And right, so that's MMBs. So now just here in text again, so the basic rule that we're going to be using is that we're going to be splitting into multiple mountain ranges, and we still do our right, and then each range, we always put the mergeable pair at the rightmost end of the range. If there's no, or we split it if there's a gap of 2 between the peak heights, and then we bag those ranges into belts. So this is ideal, because now we've won the war that we wanted to fight. So Gabriela has gotten her way, and baby Bruno is in prison. Let's also, once again, look at a simpler data structure to just see what these look like if we add back all the leaves and the peaks. And great, now my legend over there is back. So this is for instance, for n equals 20. So we see we have all the leaves at the bottom, and then the range nodes are at the top now tied together by a belt node. This is another one, and this again makes Gabriela really happy because we're minimizing by doing the bagging of these belt nodes from left to right. We're really minimizing the distance to the most recent leaves. So for any state proof that we want for the most recent state, this is going to be much more efficient than doing this within an MMR. And let's also look at the membership proof here, for instance. So similar as with the FMMRs already before, we get this factor of 2 extra for all the leaves that we want to prove, because we're doing this the less balanced bagging process. But asymptotically, we still have O log k behavior. So this is optimal for doing proofs for recent items. Now, over here is the comparison of some of the benefits. I didn't speak about all the benefits that MMBs, all the different flavors have. Another important one that I didn't mention yet here is for prefix proofs. So prefix proofs are if you want to prove, which I don't think any light clients, or at least the ones running in bridges, do yet. If you want to prove that if you had some past state or some past route, and you get a new one, and you want to prove that the new one is a descendant of the old one, or vice versa, that the old one's an ancestor of this one, then you can prove this efficiently. So that's not one of the benefits I'm mentioning here, but the ones that I'm listing here that are, oh, this is bright. Okay, I'll try to look here and point over there. So the important ones over here, for instance, are the membership witness size, which we see, right, we see that we restored the log k behavior over there, and this should have been order k. But the other important thing that we have is the gap size sublinearity that we regain, which is if we sync up to a more recent, if we sync up the amount of blocks that we will have to process here, or the amount of, this will be more efficient than with a blockchain. We'll have to process all of the headers, so it will be order k. Cool. And of course, you wouldn't be here if you also wouldn't want to see code. So these are some places where this is implemented in various forms. So on the one hand, we've got Snowbridge, where we're currently using MMRs. which is coupled, so that's on the Ethereum side, on the EVM, and then for us on Parity, most of this lives within our two-frame palette, so the BEEFY palette and the Merkle Mountain Range palette. Those work in conjunction to then be used to provide proofs to the Ethereum side. And then we have a closure implementation on a Web3 repository that does the UMMBs, FMMBs, and the MMBs, which will be where the next step is to port those over into Substrate. Yeah, that's it. Thanks for being here, and let me know if you have any questions.
Can you give some example of how these proofs are used in real world?
How the proofs are used in?
In real world, like in production applications.
Yeah, so over here I was using these things generically. So something that we're using is if you want to prove that some block is there and you want to prove some state that lives within that block, then if these are all stored in this sort of data structure, now what lives on the, in this case for instance on the EVM, is that this thing only keeps the accumulator, which would be the, let me switch back to another illustration. So in the case of MMBs now, for instance, it would only be keeping this particular belt node over there. And if you tell it, oi, like prove some item to me, then what you would what you give to it as a proof is everything that lives on the code path of some leaf. So that's what I was illustrating here, for instance. So that's everything here marked in green, these proof items. So then you can prove. So then on the light client, you only have to store this accumulator, which is constant size here, or for the UMBs as log n. So you can very efficiently, by keeping only something, like you can provide a Merkle proof to it.
Yeah, perfect. And who provides the accumulator, for example, in EVM?
Right. So this accumulator gets updated if the authority set on the other side signs off a new one. So currently in the implementation, you're trusting that if the authority set signs a new state root, or like this, an MMR root or an MMB root, that this one descends from some old state. If, as I mentioned before, I unfortunately didn't get around to those, but if you use prefix proofs, then you can also even efficiently prove that this new state as an entire, or this new Merkle Mountain Belt or range descends from the old one.
Thank you.
I feel like a mime, sorry.
Hey, hi there. When can we expect some of these optimizations in Substrate?
Oh, that's not the question I wanted to hear.
Okay.
Soon.
Okay.
So the prefix works I still have to finish implementing, and then the next step is putting it to Substrate.
Okay, cool. Yeah.
Should I be risky and say 3 months?
That sounds good. We can do with that.
Maybe I shouldn't have said that.
We now have
It's on Gabriele,
video
yeah.
now, so like, it's scary. Any other questions?
Is Snow4 going to production with belts or ranges?
Vincent. So depends. So this is where it depends on the timing. Guess you're targeting going live in half a year or so? On Kusama. Yeah.
Our BEEFY client is upgradable, so we can just swap in a new client with Merkle Mountain Belt support.
Yeah, so, right. And the nice thing with this accumulator structure here, or at least, well, the UMMBs are a bit different because your accumulator is no longer constant size. You have to keep all the peaks. But if you upgrade this to like a Merkle Mountain Belt, the proof structure is exactly the same. So you just provide like the leaf you're trying to prove and the proof items. And in this case, because the EVM, like, it only keeps the actual, like, well, the MMR root or the MMB root in this case, and you're then calculating the, so the membership proof will still work exactly the same. It doesn't matter what the internal structure over here is. You're still, like, just taking a leaf, hashing together with its partner, then the next item in the co-path, yada, yada, yada. So that's still compatible.
Thanks. And my second question, did you look into vertical trees? Does they, like, provide some benefit for this use case?
Haven't looked at them for this use case. Should we be switching to vertical trees? No. There's a clear answer.